So this course is going to be pretty quick. It's going to be dealing with hydrology. And unfortunately, so some of this is wrong. All of it's wrong. That was from the NHI course. I apologize. What we're going to be doing here is, did you all watch I think it was an animation film about hydrology? So that we're going to go over a little bit of that and then some more. So you should have a fairly good background on the hydrology course. So what is hydrology? Hydrology is the science that deals with the occurrence and movement of water. So when we talk about hydrology, it's really about how much and how often. How much rain are we getting and how often does that amount of rain happen? It's not an exact science. It's some people in the hydraulics field feel like this is voodoo science. We don't think that. But it is sort of science and an art. And if you're interested, hydraulics is really how fast, how deep. So that's the difference between the two. How fast is that water running? What's the velocities? And how deep is it? That's hydraulics. But hydrology is how much water are we getting and how often are we getting that much water. So here's the hydrologic cycle, and I think that video went through this a bit, right? So you have condensation in your clouds. It turns into precipitation and it rains. And some of it, the water will run off and some will infiltrate. And that infiltration is called a loss because we're losing water from runoff. So runoff will go typically to your streams if you're out in the country and go to bigger rivers and all that. Or if you're on a road, it's going to accumulate on your road and either flow off it if you don't have curbs, or if you have curbs, it's going to accumulate in your gutter. And you have to do something with it. So in addition to the infiltration, we have transpiration. Do you know what that transpiration is? What's that?
Just when living stuff that uses water breaks down from trees.
Right. So the plants pick up the water and they send it into the atmosphere and transpires into the atmosphere. So something else we have is when it gets to the lake, then you have evaporation, and it goes up into the clouds where it condenses and you start the whole system over. I think that's neat, everybody. So let's talk a little bit about the rainfall runoff relationships. So total precipitation is composed of hydraulic abstractions, which are those losses, like infiltration, and excess rainfall, or direct runoff. So the excess rainfall is anything that hasn't been picked up by buildings, it hasn't gone into the ground, the plants haven't picked it up, it's anything that's actually running off, it's excess rainfall. So these abstractions, like I've been saying, they remove a portion of the falling rain, and that just so it doesn't turn into runoff. And whatever is the excess is the runoff. So what's an abstraction? The biggest one that we're really, this is the only one we're really going to go into any depth in, is infiltration. It's just water percolating into the soils. The rate depends on the soil type you have. Is it sandy? Is it clay? Is it silts? That determines the rate that the water will go into the soil. Also, are you on a steep slope or a mild slope? What do you think is going to happen on the steep slope? Will you get a lot of infiltration? No. Gravity is going to take it away, right? Vegetation, if it's highly vegetated, will there be a lot of infiltration?
Yes.
Could be, depends on how much rain you get, right? Or it could be like the Amazon where it just falls on all the trees, something like that. Moisture content of the soil. Is the soil really dry? Have you been in a drought? Well, sometimes if you have super dry soil, the water will run off because it can't take it up. It can't absorb it so fast. After a while, as it starts absorbing water, it will take more and more with it. And temperature. You get snow here, right? So you think you have much infiltration once the snow happens? Not immediately anyway, right? And precipitation intensity. We're talking inches per hour. How much are you getting? Is it a quarter inch in an hour? Is it 5? You know, like in Texas, what did they get, like 10 inches an hour for 48 hours or something with that hurricane a few years ago? So all of this determines how much infiltration you have. And the other thing, well, we'll get into that in a second. So this is the largest abstraction that you're going to have. Oops, that looks like it. Right, no, that's a duplicate. So there's no one single infiltration model that is commonly accepted to determine what the infiltrate rate is or the volume of infiltration. But this is one model, the Horton model, that we can show that is an infiltration model. So what we have here is the green is the infiltration. This is our line of, what can I call it? It's the infiltration capacity. So what it's really saying is that when a storm first starts, infiltration is really high. As the storm continues, the infiltration rate goes down and down until it reaches some steady state where the amount of water that's infiltrating is constant. And almost every soil will do that. It just depends on those other parameters, how fast this happens when you get to that steady state. So anything above the line is excess water. And anything below the line is infiltrated into your soils. Any questions?
What's the blue dotted line?
This is the steady state line right there. And so you can see that as that storm happens, it'll go to the steady state and then it just keeps on going. So let's look at the effect of watershed characteristics. How do you think a drainage area would affect the amount of runoff you get in a drainage area? Do you think is it always going to go up? Does it depend on the size of the drainage area? Yeah, sure it does. So the runoff does depend on your drainage area. If you have a small area, you're going to have just a little bit of runoff, right? If you have a large area, you're going to have a lot more runoff. How about slope? We kind of talked about that a few minutes ago. If you have a steep slope, what's that going to do to your runoff? Probably increase it. If you have a mild slope or a flat slope, you probably just have, especially a flat slope where it's just flat out there, you probably have depressions that might pick up ponding, water or pond. Or if it's just a mild slope, it travels, but it goes very slow. How about roughness? You know what I mean by roughness? Is there a lot of vegetation? Is there a lot of riprap out there? That kind of stuff. So the higher the roughness, what happens to the velocity of the water? Decreases, right. And storage, we're talking about that ponding that you see. It's not something that you created, like a detention pond or something like that. It's the natural variations in the landscape. So if you have a lot of that, variations in that landscape or water might pond, what's it going to do to your runoff?
Decrease runoff.
That's right.
There's just ponds in there, it just stay there instead of moving.
Yeah, and it'll stay there until it rises too high, and then it might start moving as it goes over the edge, right? Great. Do you know what drainage density is? It's really the length of your, what is it? I think it's, do you have it there? Drainage density? It's the length squared over the area. I think that's what it was. It's the length of the channel that you can measure divided by the area of the watershed. So the more tributaries, the more little creeks and rills and things like that, the more drainage density you have. Sometimes the Army Corps has gone in there and dug out channels and straightened them out, and that will affect your slope, your discharge as well, your watershed characteristics. Because if you look at a natural channel, what do most of them do?
Meander.
They meander, and if you're in flatter slopes, they can be huge meanders. And that is nature's way of slowing down the velocity of the water. Longer length, or, you know, if you looked as the crow flies over that distance. So you're doing this, and it slows down the water. When the Corps goes in there and they just straighten these channels, or anybody else really, irrigation companies do it too, you're taking out the length, but you still got the same slope over that distance. So that increases your velocity quite a bit. And that impacts how you're going to design the structure. Antecedent moisture content. We talked about that a little bit, didn't we? I didn't use that term, but who thinks antecedent means after? Who thinks it means before? Okay, a few of you who just don't know. It means before. So that was good. Nobody answered after. It means the before moisture, before the rain falls. What's the moisture content of the soil? And so if it's fairly dry, it might soak it up. If it's super dry, like out in the desert, have you ever seen those videos on Discovery or USGS? You know, the rain hits the desert and bounces away, right? So maybe you had a storm 2 days ago, and that's going to affect your runoff and the next storm if it just happened today. And you have other storms because the ground's already kind of. Although I'm saying that, but we really don't take that into account. Not too much. So here is looking at a drainage area. And everything is equal here except the size of the drainage area. So the intensity of the rainfall, that hydrograph is what we call that, is the same. And it's raining across the entire watershed on both of them. So if we look at that, what would you expect to see? Do you guys know what a hydrograph is?
Yes.
Yes? Everybody shaking their head? Anybody not know? Let's ask that. It's, okay, so it's a, so it's discharge versus time. And in this next slide, this is the effect you'll see from these two watersheds. So the red line is the hydrograph from watershed A, which is the larger drainage area. And you can see that even though the hydrographs start at the same time, because we have the same intensity, it moves along, but the larger drainage area has a higher peak. And it comes later than the smaller drainage area. And then it also lasts longer along that timeline. Watershed B has a smaller peak. It's pretty much the same, but it's a smaller watershed, so it peaks earlier and the hydrograph ends earlier. So if you look at that, we're saying for these two scenarios, large area, small area, we're getting these hydrographs. So what I need some volunteers, because what we're going to do is look at the effects of drainage density, storage, roughness, slope, and antecedent moisture content. And what I want you to do is in your book, you see it, that first one is slope. It gives you the what you should be looking at. One is a steep slope, one's a mild slope. And what I want you to do is go up to the page that says slope and draw the hydrographs, just like this, but for that scenario. Great. Nick, which one do you want to do?
I'll do slow.
Great. Okay. So roughness, who wants to do that one? If you don't volunteer, I'll volunteer you. It's a big one there.
Markers.
Yep. Oh, you can use one color, that's fine.
Uh-oh.
Anybody want to volunteer?
I'll do it.
Great.
Here's the,
Hey, Steve, which one do you want to do? Roughness?
yeah, I'll do it.
Okay. I need somebody to do the effects of storage. Great. Andrew. And then we have drainage density. Yeah, okay. I'm sorry, how do you say your name again?
Absolutely.
Abdullah, right? Abdullah, great. And then the last one is antecedent moisture. One more volunteer. Everybody's looking down. How about somebody from that last table? Great, thanks. And when you're done, just stand by your artwork. Abdullah, you're going to need a real marker because we can't see that. And while you're sitting in your seat, you can draw these yourselves, you know.
Are we doing this for both the small and the large area?
Well, it's for the roughness from your book. They
Right,
give you the
okay.
example, yeah.
That's what. In just a particular category.
Okay. So why don't we start off with slope? So we had a steep slope and a mild slope, right? And why don't you tell us why you drew it this way?
Because, like we said, the mild slope, it moves a lot slower, and there's a lot more time for the water to infiltrate into the soil. The runoff hydrograph of the mild slope will be a lot smaller than the steeper slope, where water's just zooming on by,
Okay.
and that leads to greater discharges.
Okay. So on a mild slope too, you might want to think that maybe it wouldn't come up so fast.
Yeah.
It will be smaller, but it might be something like that.
Okay.
Okay. So it just takes a little longer to get to that peak, and it takes a little longer to go through the whole hydrograph. Okay, how about roughness?
I'm not much of an artist.
That's okay.
So ignore this line too. On the smooth surface, the discharge is going to run off faster, so it's going to peak higher earlier and then trail off. And if it's rough, it's going to slow it down, so the peak's not going to be as high, but I think it's going to last longer.
Okay.
This will probably taper out a little more than I kind of got it going like a hump.
You've got the general
General
idea.
idea.
No, you did a good job. Because what he's showing is that the peak on the roughness one is later than the peak on a smooth slope, and it's lower. And also, like you said, it's drawn out. The hydrograph is drawn out for a rougher slope.
The question, then the
Yeah.
area under these two curves is going to be the same, right? You can still have the
Should.
same amount of water.
Yeah, it's just roughness,
Yeah,
yes,
yeah.
yes, yep. Yeah, the area under a hydrograph shows the volume. You can actually calculate the volume under the hydrograph. So you guys can sit down if you like. Thanks. Okay, storage.
With the normal slope, just a normal hydrograph. For the storage, I felt like it would drag it out a bit longer, but as I think more about it, with basins, would the hydrograph have a lower peak?
Yeah.
Okay.
Yeah, so he's showing, it is a little bit lower, but it might be lower than that. So if you have storage, it's holding water back, so your peak isn't as high. And, yeah, so the hydrograph itself might look the same, except that the peak would be a lot lower. Right? Thanks. Drainage density.
Yeah,
I like
I
it.
really understand it, and A has more density, so it's more runoff. So it's more bigger peak than B, right?
Okay, so A had a lot more tributaries and things like that. So because there's not a lot of overland flow, it doesn't have to go so far. Water gets into those tributaries and into the main stream a lot sooner than it would with an area that doesn't have much stream length, no tributaries. It's a lot of overland flow that takes a long time to get to the channel. So the only thing I might say is, because this takes longer, your peak would probably come over here. It would take longer, something like that. Yeah, how about if we do something like this? It might be something like that. That's okay. Good job. I think that's mine. Thank you. And then antecedent moisture content.
Just going on with what we've talked about so far, drier soil, it's not going to try to absorb the water as much, so it's going to have a higher runoff, probably for a slightly longer period of time. But with saturated soils, it's going to try to absorb the water more, so we're going to lose more of our runoff, and so that's why it's going to have less peak.
Yeah, okay. Generally, that's correct. But, you know, when I say dry soils, I'm talking deserts when it doesn't pick it up. So if in this state, maybe you haven't had rain for a week or two, it's not going to be that dry. It will pick it up.
So we'll have more or less the same, maybe a little less.
Well, and it depends on when your runoff was, or your previous storm was, how wet your soil is. So if it's saturated soil, you're going to get immediate runoff. And if not, it will absorb it some. But in a desert situation, that is true, what you've got there. You have a dollar. If you're looking at it as, and my apologies, I confused you guys. So if you had just normal dry and normal dry stuff, and you had saturated soils, what I'm trying to say is, you would have something like that. You would have a pretty high peak, and on the dry, so this is B. And then for dry soils, it would be something like that. It's picking up more because it is drier. It's not desert. Yeah, but you did a good job because you did what I was talking about, and I should have clarified. So, there you go. Are there any questions about these? Everybody get it? Okay. So I know this was done over in that video you saw, talking about recurrence intervals. What I want to stress here is that the recurrence interval is the average time period in which a flood of a given magnitude can be expected to be equal or exceeded. So if I say a 10-year storm, are you only going to see that storm, that 10-year storm, once in 10 years? No. That's on average, that's when you'll see it. But, you know, these days, that's not so true. It's even less true. The actual probability of seeing that storm is this little equation, which says the probability is equal to 1 over the return interval. So if I said a 10-year storm, the probability of seeing that in any given year is 1 over 10, so it's 10%. If I said a 2-year storm, what would be the probability of seeing a 2-year storm in any given year? 50%. Exactly. That's what exceedance probability means. So if I'm saying a 100-year storm, on average, you will see that storm 1%. You have a 1% chance of seeing it in any given year. On average, you'll see it once over 100 years. Okay, so people get that mixed up. They think in a 100-year storm, when you just saw 2 in 5 years, what's going on? Well, it's because you have a 1% chance of seeing it in any given year. Okay. Any questions?